So in the last class, we were discussing about the analytical expression for quantization, where we had seen that considering the optimum mean square criteria, we had made the derivations for the analytical expression involving the quantization error, and we also discussed the aspects of non-uniform sampling and non-uniform quantization, and there we had discussed that when and why should we go in for non-uniform sampling and non-uniform quantization. Now, with all these basic knowledges, we will now proceed to the next topic of our discussion, which is regarding the basic relationship between the pixels. Now, this is what is going to be the topic of today. Now, in this, primarily we will be talking about the relationships which the pixels will be having with respect to each other. Okay. Let us take a grid which we have shown over here. Okay. And here, let us consider a particular pixel with a coordinate x, y. Okay. So we are considering a pixel, let's say a pixel P having coordinate x, y, and we are going to consider its relationship with respect to others. Now, the first definition which we have in this connection is the definition of a four-neighbor. Now, given a pixel xy in this particular position, the four-neighbor is defined as follows. If we consider the pixel which is immediately on the top of it, the pixel which is immediately on the bottom of the pixel under consideration, the pixel which is immediately on the left, and the pixel which is immediately on the right. Okay. This constitutes the four-neighbor for a pixel. So this is the given pixel, and its four neighbors are immediate top, immediate bottom, immediate left, and immediate right. If I write in terms of coordinates, then for the pixel having coordinates x, y, its four neighbors will be the points x minus 1, y, x plus 1, y, x, y minus 1, x, y plus 1. Is that clear? So, these are the four neighbors. Now, what are the other neighbors that this pixel can have? Obviously, you can see that there are pixels here, 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 everywhere there are, this entire grid can be assumed to be filled with pixels, and we are not considering all these diagonal neighbors in the definition of four neighbors. Okay. Let us say this set of four pixels, that is the immediate left, right, top and bottom, these four pixels, they belong to a set N4 of P, where P is the given point, given pixel over here, and we are considering its four neighbors, and this 4 points x minus 1 y, x plus 1 y, x y minus 1 and x y plus 1, all of them belong to the set N4 of P. Okay. So this is the set of all the four neighbor pixels, right? So this excludes the diagonal neighbors. Now let us define yet another set of pixels, okay, where we consider the central pixel over here, and we consider this one, this one, this one, and this one, which means to say we have taken the 4 diagonals, and we are having pixels having coordinates of x plus 1, y plus 1, x minus 1, y minus 1, x plus 1, y minus 1, and x minus 1, y plus 1. These 4 pixels, I say that they belong to a set n suffix d p. The suffix d stands for the diagonal neighbors. So these 4 points are the diagonal neighbors. Now if I make a union of the set n4p, if I take its union with ndp, then what do I get? I get 8 neighbors. I get these are the 4 diagonals, and in n4p I have got the immediate top, down, left and right. And taking the union of these 2 sets, what I will be getting is, if this is the given pixel, then this one, this one, this one, this one, this one, this one, this one and this one. So all these 8 pixels, they are forming a set which I am calling as N8P. Okay. So this N8P is composed of the union of the 2 sets N4P and N8P. And all the pixels which are belonging to this set N8P, they are defined as 8 neighbors. All the pixels in the set N8P are defined as 8 neighbors, whereas all the pixels in the set N4P are defined as the 4 neighbors. Is that clear? So these are the 2 definitions. So either we will be talking of the 4 neighbors or we will be talking of the 8 neighbors. Now the next definition concerns connectivity of pixels. Now to define connectivity, let us define a set of grayscale values or a set of intensity values. Okay. Let us take a set V, okay, which contains some intensity values. Let's say that this V is a set of some intensity values, say 59, 60, 61. These are some of the intensity values. And by the term connectivity, what I mean to say is that we will see that whether, taking any pixel from this set V, let us say that we take a pixel P over here. At this position we have a pixel P, okay, whose grayscale value, whose intensity value, which I am calling as f of P, okay, that belongs to the set V. So I have taken some pixel whose intensity is belonging to this set. So this is where I have this pixel P, okay, and now I will be seeing that within its 4 neighbors, okay, these are the 4 neighbor pixels for this pixel P, and if any one of them, okay, belongs to this, if the intensity of any one of them belongs to this set V, okay, then we will say that the pixel Q, if the 4 neighbor pixel which I am considering is a pixel Q, okay, then we will say that P and Q will be having a 4 connectivity. So the definition is something like this. The definition of 4 connectivity, I am considering a pixel Q, okay, which is a 4 neighbor of P, okay, and I am also assuming that f of Q, that is to say the intensity value of Q, belongs to this set V. If this is fulfilled, okay, then we will say that P and Q have 4 connectivity. Okay. Now likewise, we can have the definition of 8 connectivity. In that case, the definition is similar as before. The pixel Q belongs to the set N8P, okay, N8P we have already defined, and f of Q belongs to the set V. It is obviously assumed that f of P also belongs to the set V, okay. So if this is fulfilled, then we will say that Q is having a 8 connectivity with P, okay. The next definition, okay, combines the 4 connectivity and 8 connectivity together, okay. Let us see how it is. The next definition is on a mixed connectivity, or we call that as M connectivity. M connectivity, and M stands for mixed connectivity. The definition is like this, that if I pick up a pixel Q which also belongs to this set V. So already I am assuming that f of P belongs to the set V, f of Q belongs to the set V, okay. Then P and Q will be having M connectivity if the number one thing is if Q belongs to the set N4P. If Q happens to be a 4 neighbor of the pixel P, then obviously this pixel Q and pixel P will be M connected. They will be having M connectivity. And the second condition is that, of course, this is with an OR. So if Q belongs to N4P, it is anyway M connected. Or if Q belongs to the set NDP. What is NDP? NDP is the diagonal, the set of diagonal neighbors. Okay. If Q belongs to NDP and the set N4P intersection N4Q is empty. Empty means if this intersection N4P and N4Q, if this intersection does not give a pixel whose intensity value belongs to this set V. We will illustrate this with an example now. So if the pixel Q is a 4 neighbor, unconditionally it is M connected. If Q belongs to a diagonal neighbor, okay, if Q happens to be a diagonal neighbor, then the diagonal neighbor will be will be M connected, provided the intersection of the 4 connected set of P and 4 connected set of Q is empty. What does it mean? Let us say we have V supposing the set V consists of pixels having intensity 59, 60 and 61. And we have here a pixel P whose intensity value is, say, 59. Okay. So this is P. Now, let us say that this particular pixel, okay, which is a diagonal neighbor of this point P, is having an intensity value of 60. So, this pixel happens to be a diagonal neighbor of 59. Now, what is the intersection of N4P? I take this as Q. This point is Q, this point is P. This one is P, this one is Q. So, what is the set? What is the intersection of N4P and N4Q? The pixel which is immediately on the top, this particular pixel, isn't it? This particular pixel happens to be the intersection of N4P and N4Q. Which one more? Correct. So, you are considering this pixel, okay, this pixel, I mean, so this one is belonging to the N4Q set and also it belongs to N4P set. So, we will be examining both these pixels. Now, if I find that neither this pixel nor this pixel belongs to the set V, I mean its intensity, if their intensity do not belong to this set V, then we will be saying that the intersection set is empty and the pixel Q and pixel P will be M connected. Agreed? Supposing they are having intensity values of, say, 100 and 101. This point and this point. Let us say that this point is the point S. Okay. This point is the point T having intensity value of 101. Okay. So, this means to say that this pixel and this pixel do not have their intensity in the set V. So, the intersection N4P intersection with N4Q, isn't that an empty set? That is an empty set, and in that case I will say that Q happens to be a M connected, I mean Q is M connected to P. So, if this is empty, since this is empty, I will say Q is M connected to P. Let us take yet another example. Supposing I have pixel P having intensity 59 over here. Pixel Q having intensity, this is point P, this is point Q having intensity 60. And I have yet another pixel over here whose intensity value is 61. This is the pixel S, let us say. Pixel S is having value, pixel P having a value of 59, Q having a value of 60, S having a value of 61. Okay. Now what happens? That the intersection of N4P and N4Q, is it empty? It is no longer empty, because in this case, in this particular example, N4P and N4Q's intersection is non-empty because it leads to this point S, okay, whose intensity value is belonging to the set V. Okay. So, since this is not empty, now should I call this pixel Q M connected to P? I will not, because according to my definition, according to my definition, I have already said that if Q happens to be a diagonal neighbor of P and the set N4P intersection N4Q is empty. And since correct,
in that definition you are not mentioning that the intensity value of the pixel.
I have said, please, the question which was raised was that the intensity values were not mentioned, but this is the basic condition. F of Q belongs to the set V, F of P belongs to the set V. So that means to say that both the pixels P and Q are having their intensity values, okay, belonging to this set V. Only then the definition of 4 connectivity, 8 connectivity and M connectivity will hold good. Any other questions?
The 4 neighbor set 4P intersection N4Q. You are matching you are taking the intersection of the intensity value.
Yeah.
Intensity is not important when we say 4 neighbor set. 4 neighbor set does not check intensity, it just says which are pixels.
Correct. So I will be checking in this case because the connectivity is defined with respect to the intensity over here. Okay, I will be defining this set, okay, with respect to its intensity value. Okay, so this intersection is empty means that the intensity value of the pixels which are falling within the intersection, whether their intensities are belonging to this set V or not. That is what I am going to check.
We are not giving that information. In our definition, we are missing that information.
Correct.
Yes. So you are saying that in my definition of 4 connectivity, whether I am including that. Okay, means this is the connectivity definition, but in this case, I mean this is no neighbors. Are you talking of the neighbor definition? You are not talking of the neighbor. So you are talking of the 4 and 8 connectivity. So 4 and 8 connectivity also I have included this, that in order that if that P and Q have 4 connectivity, both F of P as well as F of Q must belong to this set V. Agreed? 8 connectivity also the same thing is there. Okay? So the definition of connectivity, whether it is 4 connectivity or 8 connectivity or M connectivity, must include the intensity value set. Okay, that is why all these connectivities are defined with respect to this set V. Is that clear to all of you?
Sir, I have got 2 doubts, sir. So
Yes,
first
please.
thing is, how do we define V, sir?
The question that has been asked is, how do we define this set V? Well, that will be specified by us. So whenever we are talking of a connectivity with respect to a set of intensity values, we will be specifying the set of those intensity values and then we will be defining the connectivities. So if I say that I want to find out the connectivities of pixels having intensity value of 59, 60 and 61 within this image, then I will be searching for this connectivity, okay, in this image space, and I will be finding out that wherever I have got a pixel P whose intensity belongs to this set V, I will be finding out that whether I can find another pixel Q, okay, in its 4 neighborhood or in the diagonal neighborhood fulfilling the M connectivity property, or whether they are 8 connected or whether they are 4 connected. So the connectivity is very much linked with the set of intensity values.
In this definition of M connectivity, we have defined N4 of P intersection N4 of Q is phi, sir.
Yes.
But
I think it shouldn't belong to V. That's all, not phi.
It should not belong to V. It should not
Okay,
belong to
otherwise
V. So yes. So if it has created any confusion, please make a note of it over here, that this intersection of N4P and N4Q, okay, gives you a pixel whose intensity does not belong to this set V. Okay.
Sir, or we take one more is intersection of V, and that we call empty. Then will it be okay?
Correct. That also you can take. You can take the intersection with, I mean, you can take the set V also in this process. Okay. So is the definition of M connectivity made clear to you? Okay. Now, let us have the next definition, that is the definition of adjacent pixels. Okay. Now, a pixel P is adjacent to a pixel Q if they are connected. Okay. So, likewise, we can define the 4 adjacency, 8 adjacency or M adjacency. So, it could be a 4 adjacency, 8 adjacency or M adjacency. Okay. Now, we can also define the adjacency of 2 image subsets. Let us take a subset S1 of any image, and we take another subset S2, and we will say that the image subset S1, okay, this is S1 is an image subset and S2 is an image subset. So, we will say that S1 is adjacent to the subset S2 if any pixel belonging to this image subset S1 is adjacent to any other pixel in the image subset S2. If any pixel belonging to S1 is adjacent to any pixel belonging to the image subset S2, then we will be saying that the image subset S1 is adjacent to the image subset S2. Is that clear? The next definition is about path. Let us take a pixel P having coordinates x and y, and we take another pixel Q having coordinates s, t. Okay. Now, the path from the pixel P to the pixel Q is defined, okay. The path is defined as a sequence of distinct pixels. So, path from P to Q is a sequence of distinct pixels with coordinates. I am writing the sequence now: x0, y0, x1, y1, etc. up to xn, yn. Now what is x0, y0? x0, y0 is xy, that is to say the starting point. Starting point is P. So x0, y0 is xy. What is xn, yn? xn, yn is the end point, which is ST in our case. And the next condition is that xi, yi is adjacent to xi minus 1, yi minus 1. Okay. So if this property is fulfilled, if the sequence of pixels which I have formed in the path, okay, if they are consecutively adjacent, if the consecutive pixels in the path are adjacent, okay, and if the starting point is what we want over here, and if the end point Q is over here, and if xi, yi happens to be adjacent to xi minus 1, y minus 1, then I will define this entire sequence from x0, y0 to xn, yn as a path from P to Q. So it means to say it's like this. The question is that what kind of adjacency? Again, I can define the path by specifying the adjacency. I can specify a path with 8 connectivity or with 8 adjacency, and in that case the path will be something like this. Like say for example, I take a pixel xy over here, and I have some pixel, okay, having coordinate st over here. This is the point P, this is the point Q, and by path I mean to say it's like this. If I have a sequence of pixels like this, okay, if I have a sequence of pixels in this manner, okay, then I will be saying that this is a path from P to Q. The sequence of pixel begins with this point P and it ends with the point Q. So this is x0, y0, this is x1, y1, this is x2, y2, x3, y3, x4, y4, x5, y5, x6, y6, x7, y7, x8, y8, x9, y9. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and this of course is the 10th one, okay. So this is the chain of pixels which I have. Now in this case, this is the sequence 0 to x0, y0 to xn, yn. Then what is the length of my path? The length of my path is, somebody has said n plus 1. It is not exactly n plus 1. The length of the path is only n. Okay? Because, just see, there are how many pixels specified over here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are totally 10 pixels. But I calculate the path 1, 2, 3, 4, 5, 6, 7, 8, 9. At the end of 9th portion, I have reached the destination Q. Okay. So my path length in this case is equal to 9. Okay. Okay. So path length is n. Now then,
Pardon?
Yeah, 10 points. Gravity and 0. Start from 0.
We have 10 points, okay? But 10 points are being specified as x0, y0 to x9, y9. Okay? So n is equal to 9 and my path length is 9. Is that clear?
the next definition is on distance measures. So we take 3 pixels. We take a pixel P having coordinate x, y. We take a pixel Q having coordinate S, T, and we take a pixel Z having coordinates U, B. We take 3 pixels. And now I am interested in defining the distance between the point P and the point Q. So it is something like this. I have a point P over here, I have a point Q over here, and I am interested in finding out the distance between these two places. Now what kind of distance am I looking for, and what are the various definition of distances that we can have in the digital images? This is what we are going to study. Now one simple distance measure could be that I take the simple Euclidean distance between this point P and the point Q. But over and above this Euclidean distance, we can also have other distance measures. But whether any particular distance measure will qualify as a distance measure or not, okay, is defined by certain condition. Okay. So we call D to be a distance matrix, okay, to be a distance metric if it fulfills certain properties. If it fulfills which properties? First is that if I take the distance between P and Q, assuming that D is my distance metric, okay, any distance function, it's a distance function I am considering between P and Q, and so that D qualifies as a distance function, can you tell me that whether this D of PQ should be greater than or equal to 0, or it can be less than 0 also? It cannot be. Any distance metric, okay, will not qualify as a distance metric if it happens to be less than 0. So it has to be greater than or equal to 0. Normally greater than, but under which case should it be equal to 0? When P and Q happen to be the same points, then dP of Q is going to be equal to 0. So dPQ is equal to 0 if and only if P is equal to Q. Is it clear? Then the second property is that dPQ and dQP, how they should be related?
They should be equal, because whether I am taking the distance from P to Q or from Q to P, it should be one and the same. The third property is that D, that is the distance measure
Between P and any other point Z. Z I have defined over here having coordinate UV. Okay. That should be less than or equal to D of PQ plus D of QZ. So, if the function d can fulfill all these three properties, okay, then only it qualifies as a distance measure or a distance metric. Okay. Now we will define the various kinds of distance metrics. The first definition is on Euclidean distance. Obviously, the distance is between the points P and Q, and you remember P is having coordinate x, y, Q is having coordinate s, t. Okay. And the Euclidean distance dE of PQ. So, Euclidean distance measure I will be writing as dE, d suffix e, that is equal to simply x minus s square plus y minus t square, this whole thing to the power half, square root of this expression. This gives us the Euclidean distance. There is yet another distance definition, and that distance definition is called as the city block distance. And the city block distance is written as dPQ, with d having a suffix 4. I will tell you why it is 4. Okay. And the definition of city block distance is between points P and Q, it is mod of x minus s plus mod of y minus t. This is defined as the city block distance. So, which means to say that if I have a pixel P over here, okay, and if I have a pixel Q over here, P is the red one, Q is the green one. What is their Euclidean distance, assuming that each of these sampling grids are unit space apart? The Euclidean distance between this red pixel and this green pixel is equal to root 2, okay, because each grid is of unit size. But what is going to be the city block distance between this red and this green pixel according to this definition? It is equal to 2. So, that means to say that if I want to travel from one pixel to any other pixel which is lying over here, I can't travel diagonally, I have to travel first this distance and then this distance. If I do that, then I will be traversing a total distance equal to 2, and that is what my city block distance defines. This is the city block distance definition. So, if I have a pixel over here, okay, whose distance I am denoting by 0, means this is my starting point. If this is my starting point and I apply my city block distance measure, what is the distance for this pixel? Pixel immediately to the left, 1. Immediately to, immediately on the top, 1. Immediately on the right, 1. Immediately down, 1. What about the distance of this pixel? 2. Here 2, 2, 2. What about here? 2 pixels up, 2. Here 2 pixels on the right, 2. This one again 2, this one again 2. What is the distance of this pixel? Just think of whether it is 4 or 3. 3, obviously, because it is x minus s plus y minus t. modulo x minus s plus modulo y minus t. So I can travel from this city to this city in 1, 2 and 3 steps. So this is 3, this is 3, this is 3 and this is 3. Okay. So likewise you can keep on filling up this matrix, and this will give you the city block distance function. This is the city block distance matrix, taking this to be the starting point. Is it clear? So you find that if I adopt a city block distance, then at least for the points lying on the vertical or the horizontal grid, I am estimating the correct distance. It is equal to the Euclidean distance. But whenever I am going over to any diagonal pixel, okay, am I overestimating the distance or underestimating the distance? I am overestimating the distance, because the Euclidean distance is equal to root 2, 1.414, something like that. Whereas the city block distance is going to be 2 for the immediate diagonal neighbor. So I am overestimating the distance. I can use yet another metric, and that is called as the chessboard distance. The next definition is chessboard distance.
D4 only?
Yes. The question that was asked is why it is called D4, because the distance function is defined, okay, with respect to the
4 neighbors here. I mean, that means to say the 4 neighbors is having distance equal to unity, okay. But once you deviate from 4 neighbors, the distance is more than 1, okay. Whereas in the case of chessboard distance, it is like a king's move. The king can move 1 step up or 1 step down or 1 step to the left or 1 step to the right or 1 step diagonally up, diagonally down, diagonally left, diagonally right, like that. There are 8 possible spaces where a king can move in a game of chess, okay. And we define the chessboard distance like this: d pq, this is written with a suffix 8, and the definition is, this is maximum of mod of x minus s mod of y minus t. So out of mod of x minus x and mod of y minus t, whichever is maximum should become the distance over here. So I take a pixel having distance 0 over here. This is my starting point. The pixel immediately on the left is having a distance equal to, I mean, if I am calculating the chessboard distance, what should be the distance here? 1. Here, immediate top, immediate bottom. This is what we got in the case of city block distance also. But in city block distance, I was getting this distance as 2. In chessboard distance, what should it be? 1. Because in this case, if I take this pixel to be my Q and this pixel to be P, in that case, clearly see that x minus s is going to be equal to 1, y minus t is also going to be equal to 1, and I am going to take the maximum of 1 comma 1, which is 1. Whereas in the previous case, it was mod of x minus s plus mod of y minus t, and that's why I was getting distance equal to 1 plus 1, 2. Whereas in this case, all the 8 neighbors will be having a distance equal to unity. Now take this neighbor, this is having 2. What about the distance of this? 2. What about the distance of this? 2. 2, 2, 2, 2, 2, 2. Okay. This is how my distance matrix will look like. So in this case, am I underestimating the distance or overestimating? I am underestimating the distance, because I am calling here that the diagonals are having a distance equal to unity.
Whereas in the case of the earlier thing, that is to say, in the case of city block distance, I was having overestimation. I was calling it to be distance equal to 2. Whereas the actual Euclidean distance is 1.414. Now the question which you can raise is that
why we are not following this Euclidean distance? Instead of Euclidean distance, why at all we are considering the city block distance or the chessboard distance? Well, just see, in the case of chessboard and city block distance, the distance measures are always integers, and it is convenient to represent everything in the form of integers when you are dealing with image processing. Okay, this you can store in a matrix of integer values, all these distance functions. Whereas if you are taking the Euclidean distance, it is not giving you the measures in terms of integers, those are becoming real values. So in image processing, we will be considering all these different distance functions, the chessboard, the city block, as well as at times we will be considering the Euclidean distance also. Okay. So any queries or doubts related to the distance functions? Okay.
What to is chessboard distance? Its name indicates chessboard, so chessboard. Why it is city block? Is there any?
why it is called city block? Well, I don't know the reason that why exactly it is called a city block. The only thing I can think of is that
It is like, I mean, if you are going from this city to this city, then you are traveling in the form of a block like this. This is the way you have to travel from city to city.
With blocks within a city, and each block, around each block you've got roads. These grids.
Because you don't have direct roads.
Right. You can't cross through the block. You have to go around the block.
Because in between there will be some buildings also.
somebody has said that we cannot cross through blocks, and I think that is very important. That if
We consider all these to be the blocks. Okay. His argument is that if I have to travel from here to, from this place to this place, okay, I can't travel through the blocks. I have to move around the block, either this way or this way. So this can justify the naming of city block.
any other question?
Is there any mathematical relation between all these three distance measures?
Mathematical relationship between all these three distance measures. Well, I have
Already defined their relationships in terms of mathematical expressions. This is the chessboard distance metric, this is the city block distance metric, and Euclidean you already know. Okay.
Block distance. Is there any formula so that we can directly get the Euclidean distance?
no such direct conversion.